Welcome to UGC lecture series Linear Integrated Circuits. So, in this lecture we are going to discuss about the differentiator and the integrated circuit. We know that the operational amplifier is called as op-amp or operational amplifier. 741 is called as operational amplifier since it is used for performing the mathematical operations such as adder, subtractor, differentiator, integrator, logarithmic, anti-logarithmic values, multiplier, divider. So, it is called as an operational amplifier. We have seen the adder, subtractor circuits, differential amplifier circuit, and now we are going to see the most important applications of the operational amplifier as a differentiator and integrator. So, this is the circuit of differentiator. It is an ideal differentiator which has two passive components. The capacitor is connected in between the signal and the negative input terminal, and the output is fed back to the input through the resistance R. So, this is the basic differentiator circuit. So, now we have to derive the gain of the circuit, or you can also say the output of the circuit from which we can derive the gain. Consider the current through the capacitor as IC and the current through the resistance as IR, and take this as node A. KCL at node A gives you IC plus IR is equal to 0. So, what is IC? It is the current flowing through the capacitor C. So, you can write it as C dVi by dt plus the current flowing through the resistance R is given as V0 by R is equal to 0, from which you can calculate output voltage V0 by R is equal to minus C dVi by dt into R. And if you see the equation, the output voltage is RC, multiple of RC times the derivative of the input signal. So, this is the time constant of the differentiator now. And if you write it in the S domain, you can write it as V0 of S is equal to minus RCS. S is actually the frequency term. It is replaced by j omega, and omega can be replaced by 2 pi f, and so the capacitor is actually treated as a frequency term. So, you have to include a S for each and every capacitor in the circuit, and so it is RCS Vi of S. So, this derivative part will be replaced by Vi of S in S domain. So, from which the gain can be calculated as V0 of S by Vi of S is equal to minus RCS, and here this S can be replaced by j omega. Instead of omega, I directly substitute 2 pi f. This is actually written as mod A. If you take the modulus value, then the negative sign, everything will go off, and the imaginary part is also replaced. You know that for a modulus value, you will be getting only the magnitude of the equation. So, you have R C 2 pi f. This can be written as f by Fa, where Fa is 1 by 2 pi R and C, R into C. So, this is the gain of the differentiator, which is written as f by Fa. So, if the frequency is, when you look at the frequency response of the differentiator at Fa we have derived now it as 1 by 2 pi R C. R is the feedback resistor and C is the input capacitor, and this Fa, at this Fa it touches the 0 dB line. This x axis can take the values of the frequency of the input signal, and the y axis can take the voltage gain of the differentiator circuit, and if the frequency is increased to FA, this is FA, the gain of the differentiator will be equal to 0. So, now when you see the equation, A is equal to F by FA. If F is equal to FA, then the mod value is 1. If it is in dB, then it is 0 dB. If you increase the frequency again, if you increase the frequency of the input signal, this is the input signal's frequency. If you again increase the input signal, it is increasing at the rate of minus 20 dB per decade. What do you mean by dB per decade? It is, decade is 10 times increase in the frequency and 20 dB is here. 20 dB, 20, 40, 60, 80, these are the rate of, actually the gain is in dB, represented in dB. If you increase 10 times of frequency, then the gain is increased at the rate of minus 20 dB. For every 10 times increase in frequency, the gain is increased again and again at the rate of minus 20 dB. So, what will happen if the frequency is very high? If the frequency is very high, then the circuit will get a stability problem. So, the gain will be increased at the rate of minus 20 dB per decade. If the frequency is very high, the gain is also increased beyond the limit and it goes to instability. So, it breaks into an oscillation after one point of frequency. And also, if the frequency is very high, the capacitor at the input, for the effect of the capacitor at the input is very low. Since the frequency is inversely proportional to the capacitive reactance, if the frequency is high, then the capacitive reactance is low. Then the differentiator circuit will be very sensitive to the high frequency noise in that case. So, these are the two limitations in the differentiator circuit. The one is, if the frequency is very high, if you increase the frequency of the input signal beyond the limit, beyond FA, then the gain will increase at the rate of minus 20 dB per decade, and after some time for high frequency, the differentiator will break into oscillation, and if the frequency is increased, the capacitive reactance is reduced, and if it is reduced, then the circuit will be very sensitive to the high frequency noise. So, these two factors must be think over it, and we have to reduce the effect produced by these two factors by using a practical differentiator. So, in the practical differentiator, the two passive components will be connected in the ideal differentiator. In the ideal differentiator, we have a capacitor at the input side and the resistance is connected here. Say this is R1 C1 and this is Vi, and at the feedback already we have a resistor and say this is RF, across which there is a capacitor, say this is CF connected to the output. So, this is a practical differentiator circuit for which we have to calculate again the gain of the circuit and how the circuit is used to overcome the limitations produced by the ideal differentiator. These two passive components CF and RF are in parallel. So, this is considered as the ZF, the parallel combination of CF RF. So, it is calculated as RF into 1 by CFS divided by RF plus 1 by CFS. So, which is simplified as RF by CFS divided by RF CFS plus 1 by CFS. So, here these two terms will get cancelled. Finally, it is RF by 1 plus RF CFS. So, this is ZF and Zi is the series combination of R1 and C1. So, it is R1 plus 1 by C1S. It is simplified as 1 plus R1 C1S by C1S. If you calculate the gain, it is V0 of S by Vi of S, which is given as minus ZF by Zi. So, ZF is RF by 1 plus RF CFS into ZI is, I am reversing it. So, denominator comes to the numerator and the numerator comes to the denominator here, because ZF is V naught of S by Vi of S is ZF by Zi. It is 1 plus R1 C1 S. So, if CF RF is equal to C1 R1, then these two terms will be equal. So, the gain will be equal to minus RF C1 S divided by 1 plus R1 C1 S the whole square. So, this is the gain of the practical differentiator. The S is replaced by j omega. If it is replaced by j omega, then it is omega divided by 1 plus F by Fb the whole square. Need not to be replaced by j omega. As such, I have replaced S is equal to j omega and omega is equal to 2 pi f, and there you have 2 pi f. So, keep the f in the denominator, in this case in the numerator, and the remaining terms R1 C1 2 pi, you have to take it as reverse of that and replace by Fb. So, where Fb is equal to 1 by 2 pi R1 C1. So, in this case Fb is 2 pi R1 C1. So, here the gain is actually minus RF C1 j omega divided by 1 plus F by Fb the whole square. So, now you look at the frequency response of the differentiator circuit. Here we have calculated Fa in the ideal differentiator. Now we have calculated Fb, which is nothing but 1 by 2 pi R1 C1, and the gain which is related to this Fb like this, minus Rf C1 j omega divided by 1 plus F by Fb. So, this F is the frequency of the input signal, and Fb, that is the frequency we have derived now. So, what happens is up to this Fb, the gain is increased at the rate of minus 20 dB per decade. If F is increased, compare these two values. If F is less than Fb, what happens in the frequency response? This frequency below this Fb, the gain is actually increased. So, here if F is less than Fb, Fb is high in that case. So, the gain is actually increased since you have a smaller value in the denominator. So, the gain is increased if F is increased. Here also this F is omega is replaced by 2 pi f. Okay. So, now after this, if F is increased beyond this Fb, this dashed line is the response of the practical differentiator. So, how it is going to be reduced? When you look at the equation, if F is increased beyond this Fb, if a higher amount of value is in the denominator, which shows that this equation, this portion will be divided by a higher value. So, the gain will also be getting reduced. So, here if F is increased beyond this Fb, then the response will come to the decrease in range. So, if there is no capacitor and the resistor is connected, if this response is this continuous line shows the response for the ideal differentiator, this dashed line shows the response for the practical differentiator. So, now it is not, the gain is not going to be increased for the increase in frequency, since because we have used a practical differentiator, and also At the input of the practical differentiator, if the capacitance effect is very low for a higher frequency, we told that in the ideal differentiator the circuit will be sensitive to the high frequency noise. Now we have included a resistor at the input side, so the input reactance as a whole we have to calculate. So there will be some resistance for the high frequency noise also. So both the factors, both the limitations can be overcome by using a practical differentiator. And here there is a frequency term called FC, which is actually the unity gain bandwidth of the open loop configuration of the operational amplifier. This frequency is the unity gain, FC is the unity gain bandwidth of the open loop configuration of operational amplifier. Why I have told you that is, for designing the differentiator, we have three frequency terms FA, FB, FC, where the values of the frequencies must be FA less than FB and FB less than FC. This must be the values of the frequencies of the differentiator. Next is design of differentiator. So initially we have calculated FA. FA is actually 1 by 2 pi. With the ideal differentiator we have calculated, so it is C1 RF, and FB we have calculated as 1 by 2 pi or 1 C1, and we have assumed that CF RF is equal to C1 R1. So these are the three formulas you have to know for designing the differentiator, and the time period for the input signal must be greater than or equal to C1 RF. It must be greater than or equal to C1 RF, and so in this case C1 RF. So if this time period is very high, then these are neglected. These two factors, these two product terms are neglected, and you will be having only minus R of C1 S. So that is nothing but the gain of the ideal differentiator. So that is the first design step in the design of the differentiator. The time period of the input signal must be greater than or equal to C1 RF. And the second one is set FA as highest input frequency, where C1 must be less than microfarad. So in FA, C1 is set as less than 1 microfarad, and calculate RF. So you will have these two values, C1 and RF. Third is FB is equal to 10 times FA. You know that the formula of FB. So you know what is C1, and now you have set the value of FB as 10 FA. So FB also known. Calculate the remaining value of R1. R1 is now calculated from this value. And finally, so you have calculated R1, you have assumed C1 as less than 1 microfarad. You have calculated RF from FA, and one more value you have to calculate is CF. From these values, CF can be calculated as C1 R1 divided by RF. And if you add the OR compensation to the positive terminal of the op amp, then the value of OR compensation is the parallel combination of R1 and RF. This is the value of OR compensation. So this is the design of the differentiator. So you can design the differentiator for the value of FA is equal to 100 or 1000 hertz. So the next circuit is an integrator circuit. It performs the mathematical operation of integration. So when you look at the circuit, we have just interchanged the capacitor and the resistor from the differentiator. In the differentiator, you have a capacitor here, you have a resistor at the feedback loop. Now it has been interchanged for an integrator, and the derivation for the output of the integrator is, consider the current through the resistance as IR and the current through the capacitor as IC. Here the KCL at node A tells you IR plus IC is equal to 0, since this current is 0, and IR is represented by VI by R plus IC is given as C into dV0 by dt equal to 0. So, from here we have to calculate the output voltage. C dV0 by dt is equal to VI by R. And how will you calculate the output voltage here? So, if you have to remove this differential part, so I am using an integration for this dV0 by dt with respect to dt here minus integral Vi dt, and the constant value R is taken out, and here the differentiation and integration will go off. V0 will be equal to minus 1 by RC integral Vi dt. This is the output voltage of the integrator. So, when you look at the output equation, the output is the integral value of the input signal. So, from the circuit we have derived the output signal as the integral value of the input signal Vi. In the further classes we have to derive the gain of the integrator, so that we have to see the frequency of the input signal and how the voltage gain of the integrator varies, and what are the limitations in the integrator for the change in the frequency of the input signal. And the next is the practical integrator, why we are going for a practical integrator. These topics we can discuss in the further sessions. Draw the frequency response of the differentiator and discuss about the decrease in gain for high frequency. Integrator part we will discuss in the further sessions. So, we have discussed only about the differentiator and the limitations of the differentiator and why we are going for a practical differentiator. The references. Thank you.